Okay, so this is chapter 4 from Sebastian Raschka's Build a Large Language Model from Scratch. And this is called Implementing a GPT Model from Scratch to Generate Text. So we've covered the first 3 chapters. Actually, we skipped the first chapter, but we covered 2 and 3. So in this chapter, coding a GPT-like large language model that can be trained to generate human-like text, normalizing layer activations to stabilize neural network training. So we'll do a little few extra tricks here besides just doing the main project. Adding shortcut connections to deep neural networks, so this is important. And implementing transformer blocks to create GPT models of various sizes. So one of the components of the whole code is the transformer, so we'll do that here. And computing the number of parameters and storage requirements of a GPT model. Well, that's not too important, but we might skip that, but let's just start here. So they say in chapter 3 we already learned about multi-head attention mechanism. And well, first we started out with just attention, and then we extended that to multi-head, and we wanted to do that in a way that would allow us to have these attention heads run in parallel instead of stacking them. So we also talked about that. And once we were able to do that, we said we'd finished with the idea of a multi-head attention. And remember that when we run all of these in parallel, we get different outputs for each attention head, and then we concatenated them, and we did it so that the input to the attention mechanism or the attention head was an embedding, and actually it's a sequence. It's a sequence of tokens, so each token has an embedding, and then it can even be a batch of these sequences, but let's not worry about that right now. Anyway, it was a sequence of tokens, and each token has an embedding, or it's represented by an embedding. So, the embedding length typically is long, but in his simple example, I think he used just an embedding length of 3 or 2. I don't remember. Let's say it was 2, and let's say it was 3, and suppose we only had 2 attention heads. We say multi-head attention, but let's suppose we just had 2 heads, so not too many. But each one, the tokens are represented. The embedding size is 3. So then, as we said, we have kind of a representation coming out of the first head and the representation coming out of the second head. And what do we do with these? We have 2 outputs from the 2 different heads, and we concatenate them. But there are different ways to concatenate something that is a first of all, it's going to be a sequence. So we're going to have multiple vectors, each vector being an embedding. So we'll have a matrix, or at least a matrix. And how do we concatenate 2 matrices? So we could sort of do it, vertically, stack them on top of each other, or horizontally. So the way they do it is they, I won't draw a picture of it because we did it in the previous chapter, but the way they did it was they did it so that the dimension of the embedding increases. Okay, so that's what we said before. So the dimension of the embedding, I just said suppose it was 3, but if you kind of concatenate them across the right dimension, you get an embedding of not 3, but 3 concatenated with 3, you get 6. So the embedding increases, and that might be a good thing because I sometimes thought, well, maybe we should just take the average of the two outputs of the attention heads, but that kind of takes away from the clarity of what we've done when we average it. And this doesn't. This does. This keeps those numbers intact. We just concatenate them. So for whatever reason, that's what they do, and that's what we did in chapter 3. Okay, so we did the multi-head attention, but we haven't completed the whole deal yet, the whole GPT-like model. So now we will code the other building blocks of an LLM and assemble them all together in a GPT-like model. And then in the next chapter, we're going to train it. But first, we want to build it. So the LLM architecture referenced in 4.1, figure 4.1, consists of several building blocks. We'll begin with a top-down view of the model architecture before covering the individual components in detail. So let's look at the whole structure. So we have the data preparation, we have the attention mechanism, and we want to build the whole structure. We're going to use this and put it into here, and that's going to be called building an LLM. Then, of course, we want to train it. That's here. And then we want to do something else over there. So what does GPT stand for? Generative Pre-trained Transformer. So it must have something to do with the transformer, but we haven't finished coding. We've developed some of the parts of a transformer, but we haven't done the whole thing yet. So he says that we've already talked about tokenization and embedding and multi-head attention and even masked multi-head attention. Now we want to implement the core structure of the GPT model, including its transformer blocks, which we will later train to generate human-like text. So I said in chapter 3 we use smaller embeddings. I think we used like 2 dimensions or 3 dimensions, but that was for simplicity, just so that everything would fit on a page in this book. But now he wants to do something more realistic, and he's going to have 124 million parameters here. And that's going to be as described in the language models are unsupervised multitask learners by Radford et al. So we could check that paper, but I won't do it. He does say that in the paper they mention this number of parameters, but it was corrected later. He says in chapter 6 we're going to load in pre-trained weights, but we're not going to do that in this chapter or even chapter 5. Chapter 5 we're going to train it ourselves, but after we learn how to do that, of course we're just going to do it on a small amount of data, so it's not going to be a very good model. So once we learn how to do it though, then we'll actually just take the pre-trained weights and that were developed for the actual GPT-2 and just implant them in our model, so to speak. So then we'll have a good model. So he just reminds us that the term parameter refers to the trainable weights of the model. So we won't go into that again. So he has this picture of what GPT model does, and what it does is you put in some text and you go through a bunch of stuff, and then you get out text, but you get a predicted new token. So hopefully you predict, if you have this, every effort moves you, then maybe what you want to come next moves you forward. So hopefully your output is forward, but of course could be a lot of different things. And we want to predict some token. So this is kind of just a general picture. We do have to tokenize the text. We do have to think about embedding layers. We do have to include our multi-headed attention or our mass multi-headed attention, and that's included in some other with some other stuff to in that whole this whole section. We don't see the other stuff right here, but that's going to be called the transformer block. And then, so like it doesn't include this embedding layer part, doesn't include this, and but that's anyway. There's a transformer. Part of the code is the transformer is called the transformer block, and then we have some other stuff, some like just output layers, just plain like linear layers, and maybe some other stuff, and then hopefully we get out a prediction for a token. Now down here, he's continuing what he was saying up here, that the parameters are the weights, and he says like in a neural network layer that is represented by, so we know that layers contain weights, which and they also contain nodes, but let's say layers contain weights, and basically those weights can the application of the weights to the layer before is done through a matrix multiplication. So he says, suppose that the matrix was 2048 by 2048, then the number of elements would be that number squared, which is this number. So we would say we have that number of parameters. Let's just read this note. GPT-2 versus GPT-3. Note that we're focusing on 2 because OpenAI has made the weights of the pre-trained model publicly available. And so instead of training it ourselves forever, we can just use their weights, which we will load into our implementation in Chapter 6. GPT-3 is fundamentally the same in terms of model architecture. The architecture is nearly the same, except that it's scaled up from 1.5 billion parameters, which I don't know where he got that, but I guess somewhere before he said that GPT-2, like the larger version of, I guess there's several different versions of GPT-2, but maybe the larger version is 1.5 billion parameters. GPT-3 has a lot more, so presumably it works better and is trained on more data. As of this writing, the weights for GPT-3 are not publicly available. GPT-2 is also a better choice for learning how to implement LLMs, as it can be run on a single laptop computer, whereas GPT-3 requires a GPU cluster for training and inference. According to Lambda Labs, it would take a long time to train GPT-3 on a single, I don't know what this means, data center GPU, or 665 years on a consumer GPU. Okay, so we couldn't do that. Okay, so we're going to have a little dictionary here that's going to we're going to load it in every time we want to set up a model, and it'll say what the hyperparameters for the model will be. So like we talk about the vocabulary size and the context length, which is the maximum number of tokens that a sequence, an input sequence can have, and the embedding dimension. We said we were only using like 3 before or 2 before, but we're going to use 768 typically. But you know, we'll just have this dictionary, we'll load it in, and we can change this to whatever we want to use it, whatever we want. And then we're also going to have the number of heads, which we were just talking about, multi-head attention. So we might just have 2 heads, like I was giving as an example before, but typically we're going to have 12 heads. And then the number of layers, we said that we have a transformer in here, sorry, a transformer here, but actually we're going to have many transformers. And in this case, we're going to stack them sequentially. Now, we said that for the attention heads in here, we're going to have many of them, but we're going to run those in parallel. But the transformer block as a whole, we might have more transformer blocks, but they're going to be run uh, sequentially. But anyway, he says here that we're going to have 12 heads and also 12 transformers, or 12 layers they're called, but 12 transformers. Now, I don't think there's a reason why these two numbers have to match, or, I mean, it might be that experimentally um, it worked better, but it just seems unlikely to me. But you can look it up and see if there's any reason why these should match. But anyway, okay, so we have those numbers, and we'll have the dropout rate, and whether we're going to use bias um, in our layers or not. But anyway, we're just going to set this up and load it in, then we can change it as we like. Um, if we want to have a bigger model or a smaller model, want to have a larger context length or a smaller context length, and so on. So here he explains what all of these things are, and I don't think he says anything about why they have to be the same n heads and n layers, but you can check that out. So anyway, we're going to have this GPT, and the whole name of the whole class is initially called Dummy GPT Model. Hopefully it's not called Dummy at the end, but anyway, we're going to have a class that contains all the pieces, and it starts out being called Dummy GPT Model, and it's the backbone of the whole thing. But we're going to have a lot of different pieces in there, and initially they haven't been they're just empty classes, but of course we have to define good classes that will do what we want. So I think he says this is in figure 4.3, and this is not figure 4.3, but he's saying here we developed the GPT placeholder model to see the overall structure of the model, and next we will be implementing blocks 2, 3, and 4, and 5. So we need to do all this to fill in the back GPT model, so we can't just leave them blank, even though they're listed in here, but they're just blank, so that's not going to do any good. And these all make up the transformer block, and then like we said, we can just repeat this over and over again, like 12 times. So we get 12 transformer blocks that each one of them contain this, and run in sequence. And then we get anyway. But we want and that would all be contained in the GPT architecture, or the GPT backbone, or the what did we call it? The dummy GPT model. But then if we actually fill in the class, we wouldn't call it dummy anymore. Okay, so oh, this is figure 4.3, by the way. Okay, here's listing 4.1, and this is the structure that we're trying to build, and we have to do, take the inputs, we do something with them, then we have the attention head, and then we do some more, and some more, and some more, and then we're finished, and we just do these end steps and so on. So actually the transformer is this block here. We see there's an NX there. So we might have many many transformers stacked on top of each other. But this is the transformer. And this is our dummy GPT model. So let's see, what does it have? Um, so it has the name of it, and we see that it's um, an extension of NN module. That's very important. And okay, so we have an init as usual in any class. And then we need to have a forward method. Otherwise, none of this will work, and we can't. The PyTorch requires that we do things this way. So we need to have a forward method. And then we need a transformer definition. So right now it's just a dummy, just an empty one, but we're going to need it to fill it in, not like this. And then we also have a dummy layer norm, which we also need to fill in. So the the layer norm, because you can see there's a norm here and there's a norm here, so that's some kind of normalization process. So we need that. So that's going to be here. And each of these classes also has to have their own forward method and init, and forward method and init. And note that the dummy GPT model class does not implement the softmax layer. It stops at outputting the logits. So can we see that here? Well, we can't see it here, but we can see that there's no, well, we haven't examined it yet, but we don't use the softmax anywhere in here, so it's not using the softmax. So what happens before the softmax? So hopefully we know that the softmax converts things to probabilities. But before that, we don't have probabilities before we run the softmax. So we have what we have just prior to the softmax is uh, they're called logits. So those are the things that we are not yet transformed into probabilities, but the softmax will convert the logits to probabilities. So hopefully we're familiar with that concept. Okay, so this is the whole class, and we have to go through all of this stuff. Looks pretty awful. Okay, so here we have, I just numbered the different elements here, and here you can see like this part here um, is dealing with this 4 and 5. So, and then you can see like this part here, 8 is dealing with this, the linear, just a linear layer, and so on. So I just tried to make some of that clear here. So if you see some code here, you can try and figure out what it's trying to do over here. So anyway, we have the code. So we have to examine this code. So also here, this is all of this. So this is kind of a picture of what's going on. We start out with logits. Oh, sorry, we start out with inputs, and then we convert them to embeddings or token embeddings, and then we get the positional encodings, and then we add the embeddings to the positional encodings, and hopefully this is done in here. Otherwise, this picture is wrong. Hopefully it's not wrong. And then we do the dropout layer, and then we implement the transformer block. So this here, TRF, is the transformer blocks, and that is implemented down here. So let's see that. This is the dummy transformer block, and you can see that the TRF blocks are we do this, it's using the transformer block or the dummy transformer block, and we're actually we said we want more than one block, so we're going to use NN sequential, and then actually run a loop here. This looks like a weird loop, but run a loop here and unpack all of the transformer blocks that we're going to use. Like we said, we're going to use 12 of them. So this code here will generate 12 transformer blocks, which will be in the sequential and in dot sequential, which is fine. We can have lots of things in sequential. And in sequential is an easy way to line up multiple layers. So a lot of times we'll have um, we'll have like a neural, I'm sorry, like a linear layer, and then an um, like a ReLU function, and then another linear layer. So we might have a linear layer, ReLU, linear layer, ReLU, and bunch. We just have a sequence of them. We can usually put those all together using NN sequential. And that's what's happening here. We're putting together a whole lot of transformer blocks here. Okay, so anyway, that's what TRF block means. And we said over here that we need to do the transformer blocks. And then we have to do the final normalization. You can see it's happening over here, final normalization, TRF blocks, dropout, and adding the positional embeddings. So this is correct. This is representing what's going on in the forward method. This is the forward method for the whole GPT model. We have forward methods, inside each of these classes, but this is for the whole class called GPT model or dummy GPT model. So anyway, then we have the transformer, final normalization, linear output, logits. Okay, so that's just more explanation of this. Okay, so let's take a look at this a little bit more clearly. So of course we have these are familiar. So we said this is the name of the whole GPT model. We'll get rid of the dummy part eventually. So here's the init, and it's going to accept the CDF file, and the way that's going to be run, that's this file here. So we'll put this name in there when we call the dummy GPT, and then we can reference all of the elements of the dictionary, like the vocabulary size, the embedding dimension, the context length, the embedding dimension here. So let's take a look at what we have here. So as we said, we'll put this in here. So first of all, we want the token embeddings. And so we're going to use nn.embedding. And we have to supply it with the vocabulary size, which recall is about 55,000 or 50,000. And the embedding dimension, which I think we said is 768. And then for the positional embeddings, we need to have the context length in this case, and we need this same embedding dimension here. And we also have the drop rate for the NN dropout. And this is, as we said, going to be the transformer blocks. And again, as we said, we're using NN sequential. And this asterisk here, in this context, is the unpacking operator in Python. It's used to unpack elements from a list. So this is a list comprehension, and it's going to be here. Here's the end of the list, and here's the beginning of the list is somewhere here. And so it's going to be a list comprehension, and n layers, which is another element. We already said, like, we'll have how many transformers do we want to have to run sequentially, and I think we decided we were going to use 12. So that would be n layers up here, would be 12. And what are we creating? We have dummy transformer. We're going to create a bunch of transformer classes or I'm sorry, instances of the class. Okay, now we forgot to read this. This NN embedding randomly initialized using either a normal or uniform distribution. Okay, so that's how it starts out. So anyway, whether we're using a normal or uniform distribution doesn't really, I'm sure it has certain kinds of implications, but basically we're just setting up some random values at the beginning. Okay, and we're also going to have an instance of the layer norm or layer normalization class, and that's going to be here, final norm. And then we're going to have the final linear layer, and that's a pre-softmax. So that is this layer here, basically. And that's just a linear layer. And that takes the same embedding dimension, and the vocabulary size is here. And we're not using biases. And the linear layer output, is that what we're looking at? Yeah. So the first argument is batch size. Actually, I don't see an argument for that here for some reason. I'm not sure about this. So, we do see sequence length. So that would be the, no. Okay, it seems to me we're missing one argument because this requires 3. And here we have 1, 2, but this is bias is false. That's not really the right. It seems like we're missing one argument here. So let's see if that shows up later. Okay, so now we're going to, so that was the init method, where basically we create the architecture, the structure for the different elements, and then we put them in order here that we want to run this. So first we pick up the batch size and the sequence length from the input to the forward method. Sorry, it's the shape. So we get the input, and we get the batch size and sequence length from that. And we'll see how this actually runs a little bit later. So then we get the token, and then next, after we collect these two values, then we start with the token embeddings, which is down here. Then we take the positional embeddings, which is here. Yeah. And then we take the token embeddings plus the positional embeddings, and we add them together. We're going to call that X. And then we're going to pass that X through the drop embedding, which is up here. Drop embedding is here, and it comes from the dropout nn.dropout. So we may be doing dropout right at this point, and then we're going to pass that through the dropout layer, and then we're going to call that X, and then we're going to pass that into the transformer, and then we're going to call the result of that X, and then we're going to pass that through the final normalization layer, and then we're going to take the result of that and pass that through this linear layer here, which is, here we're taking the output of the linear layer and calling it that. They're going to take that and pass it through there, and that's going to give us the logits, and at the end we're going to return the logits. Okay, so that's a general overview. We'll see more detail as we go through this. Okay, and then we also have included the class definitions for the transformer block, the layer norm, and I guess that's it. So a little note here, the GPT model class does not implement the softmax layer. It stops outputting stops at outputting the logits. Okay, to implement these steps, we tokenize a batch consisting of two text inputs for the GPT model using the tick token tokenizer from chapter 2. So we're going to have a batch of two sequences. Here's one. Every effort moves you. That's the first element of our batch. And every day holds A. So this is two sequences, each of length 4, form our batch. So we're going to take our batch and we're going to append the first one. We're going to encode it and then append it. And then we're going to also encode the second one and append it. And if we want to see what that looks like, let's go to where it is. It looks like this. Tensor. It has 4 tokens and 2 sequences, or a batch of size 2. And these are the sequence IDs, or the token IDs. Okay, so what about this dim equals 0? Remember, dim equals 0 and torch.stack, batch dim equals 0, means that the tensors in the batch are stacked. Remember, we have 2 sequences here, or 2 tensors. We're going to turn them into tensors, and we're going to stack them. And how are we going to stack them? Along either the first dimension or along the second dimension. And it's along the first dimension, means along the rows. So we saw that just now. Here, in other words, we didn't have this one and then this one just like creating one row with 8 columns. Here we have 2 rows with 4 columns. So that's what happens when we use dim equals 0. If we had dim equals 1, I believe we would have 1 row but 8 columns, I believe. Okay, so let's look at this picture here. So we start out with an input text. Well, of course, we said we have 2, but we're just going to put in 1 at first. So we have the input text, and then we tokenize it. So we split it up like this, and then we get the IDs like this, and then we turn them into embeddings like this. So we have 4 tokens, and each one has 768 dimensions. That's what we set up. And then we're going to pass it through our GPT model. And then our GPT model is going to output 4 token, or I guess we should say 4 vectors. This is one vector, here's another vector, here's another vector, and here's another vector. 4 vectors, just like we basically input 4 vectors. So the number of outputs and the number of inputs, or the sequence length of the input and the output, are the same for our transformer. Okay, that might sound a little bit strange right now. I mean, if you think about it in terms of what we're trying to do, which is just predict a single word. So why would we do this, right? Why would we put out 4? We only want to put out output 1, actually, but we're not there yet. So anyway, we've got 4 inputs and we're getting 4 outputs. These are each element of the input is expressed as an embedding, an embedding, an embedding, an embedding. Same thing here. Okay. Then we do, so that's the GPT model, which is this whole part here, this whole thing here. Then we have to do a little bit more of this and that, so that we have to do some post-processing, and then we get our output text. And so in this example, we're getting 4 outputs, just like I just said, but it's not the same as the inputs, which is good probably, because that's how we're trying to do something useful here, not just put in an input and get exactly the same output. So we're putting in this, and we're getting out this. So you can see that if you read this, it says what? Every effort moves you, and then this says effort moves you forward. So what we're getting is the whole, or hopefully we're getting, that's what we want to get, is this whole thing, but shifted one ahead. So in other words, skip this one, and the first one will be effort, then moves, then you, and the next word, which is not present here, but hopefully it will be forward. So this is what we get. Okay. So you might be wondering, why are we outputting 4 tokens? So we can read about this on page 99. So let's read that. So that's here. Why are we outputting 4 tokens? By the way, let's just look at this, because this is just another representation of what we just saw. So what we just saw is that we have 4 inputs and we're getting 4 outputs. But then remember we said we're actually going to put in a batch of 2 sequences. So we're going to have every effort moves you. What was the other text we had? Every day whole day. So we have these together as a batch. So we should get out one result for this, and another batch, another in our output batch is a result for this one. Okay, so that's what we're going to see in the page 99. So let's see that. So this is what we get. This is just another view of what we get. So um, how is this another view of what we got? So let's just say we only got one, we only had one input, so we're only going to have one output. So that means we only are going to have, this is actually 2 outputs, but maybe that's not clear yet. But this is one of the outputs, and this is the other of the outputs. So how is this one of the outputs? That's what I want to say. So we said that that the input was a sequence of length 4, and so the output is also going to be a sequence of length 4. And again, that doesn't sound like the ChatGPT that we use, because, when we input like a sequence of length 4, we might get like an output of like, an answer could be like length 50 or length 100 or who knows what. Okay, but just hang on for a second. So, okay, but we are going to get a sequence of length 4 in this case. And what do we mean by this is a sequence of length 4? This, the number of rows is 4. So each row stands for a token, but each token has an embedding. Now, it's not the same kind of embedding that we had when we were with the inputs. Remember what the size of the input embeddings were? It was 760 something. Here, 768. That was the input when we did the embeddings at the beginning of the model. At the bottom of the model, the embedding size was 768, but we're not getting that here. So here's one embedding, and it's not 768. I mean, we don't know that just by looking at this, but it's not. It's not 768. And in fact, if you check, it's this number here. In other words, what? It's the vocabulary size. So with the embedding size at the end, if we call it an embedding, is different than the input embeddings, which were only like 768. So why is this? Why are we doing this embedding size of the vocabulary length? Because remember, the vocabulary is the set of all possible words that we could have. And so what these are sort of like a probability of um, each of the possible vocabulary. So we're trying to predict what word should come out, say in the first place, in the second token in the sequence, in the third token of the sequence, in the fourth token of the sequence. We're trying to predict what should come out, and what's going to come out is as I said, these are kind of like probabilities. They're not really probabilities, but anyway, what we want is um, the word or the token. We're going to predict the token for the first element of our sequence that has the highest number here. So like let's say among these, which is the highest? This is the highest. So, um, this is one of the words in our vocabulary. It's like if this is the 0th word, this is the first word, this is the second word. So this would say that if this was actually the highest among all these numbers, we can't see all 50,000 of them, but if this was actually the highest, then that would say we're predicting the second element of our vocabulary, whatever that happened to be. We don't know what all the different vocabulary, what their IDs are, but the second element in our vocabulary, and then maybe this is highest in this one, maybe. So that would mean we have the second to last um, element word in our vocabulary. We're predicting for the second token, and so on for all of these tokens. So, what we're going to do is turn this into softmax values. So they're going to turn them into probabilities. But still, if this was the highest logit value, these are called logits now, they're not probabilities yet. So if this was the highest logit value, then that would be that would also be the highest probability. That would also turn out to have the highest probability. So that's what we get. So that's why we get this 50,000 something as the sort of embedding dimension on the output, because it's representing all the different possible vocabulary words that we have, or vocabulary tokens that we have. Okay, and then as I said, this is just the first element of our batch. So the first sentence, which was here, but we had two sentences that we're including in our batch. We're also including this one. So we need another prediction for each token in the output of this, for this input. So that's what this second one is, okay? So that is the output. Now, okay, so but you still might ask, why are we outputting 4 tokens? I only want to output if one token, or maybe you think, oh, I want to output like 100 tokens, because when you give a prompt, you might get many, many words in the answer. But I think we all know that the way these models work is that they just predict one at a time, and then they just keep sort of predicting the next one, the next one, the next one so quickly that it looks like they're just predicting or outputting a whole long sequence, but really it's just word by word, but it's so fast. But still, even if we think, oh, we're only going to put out one, but that's not what's happening here. We're putting out 4. So why is that? Why are we outputting 4 tokens, not just one? So the answer is that this is during training. This is happening during training. So not during inference, or not when we're actually using the GPT. During training, the model outputs predictions for all 4 tokens. Because why do we do that? Because if we do that, then we can measure the error for 4 tokens instead of just one. So it's much more efficient to be able to, when we're running one text, one sequence through, we get to work with 4 different errors. We know, so that's what this picture is showing. So every effort, the prediction is this, and every effort moves, the prediction is this. So with 4 inputs, we get 4 training examples, basically. So that's much more efficient than just getting one training example. So if we only output one word, like just the last word, we could do that, but why not? Since these are already calculated, we may as well use them in our training. So we collect them, all the outputs for all 4 tokens in our output sequence, and then we can see how well we did, or how close they are. We can measure the error for each of them. So it's an argument for efficiency during training. So during training, the model outputs predictions for all 4 tokens, one for each input position. This allows us to calculate the loss for all 4 tokens simultaneously, enabling the model to learn more quickly. Remember, this is not inference yet. At inference, we will only want a single output. Okay, so that's what this picture is about. And here again, we have we have two sentences, each of 4 tokens, and that's our first batch, and that's in a tensor. And now we're going to use that is our batch. So our batch, when we print it out, looks like that. Okay, so now he's going to do a sample run. So we said that we need, for the GPT model, we need to put in this config, which will allow us to read out all these values, or read in all these values. And the model that we get, which is here, when we run this, we're going to use that on batch. And then what we get out are the logits, so we'll call it logits. So we're going to get these logits here. All of these. This is a set of logits. They're all called logits. Okay? So we're going to get those, and that's what the model outputs. So this is what it outputs. Now we'd like to know what did it actually output, but I don't know. Do we see that yet? Maybe we don't get to see that, but chances are it's going to be complete. Not chances are. It will almost definitely be complete nonsense because the model is not trained on anything. It's just been random. All the weights are just randomly assigned at this point. So we're going to put in some sequence, and we're not going to get a good prediction out of that. But this is nevertheless the process that we would follow. We'd put in the config file name. We'd get out a model. We'd apply the model to our batch, and we'd get out the logits. Okay, so now we want to talk about we've done just a little bit so far of this GPT model. We said that it looks like this, but I think it doesn't include. I think it includes this, but I think it takes this as an input, and it's does it? Yeah, it doesn't include the softmax, but it does include linear. So that's our GPT model. Okay, but we still have to fill in a lot of pieces. So, for example, we have to code the transformer block, and we have to code the layer norm. Maybe not a lot of pieces, but at least this is fairly complicated. This is not complicated to code. So the first one he does is that one that's not complicated. That is, he does the normalization class. Okay, so if you look at this, so if you think about normalization, that word normalization, I think we know we all have an idea. Of what that means in statistics or in data science or in machine learning. It means like you have some data, like here, 2, 4, 6, 8, 10. If you want to normalize these values, what does that mean? It means you take the average of them. So the average of these is 6, because it's right in the middle. So the average of these is 6. And then typically you calculate the standard deviation. So I don't know what the standard deviation of this set is, but I'll just estimate it as 2. So I would say the mean, I know the mean is 6, that's pretty clear. And let's say the standard deviation is I'll just make up a number and say that it's 2. Okay, so if that's true, then what it means is now we will convert this 6 to 0 because it's right in the middle, and we'll convert this 8 to 1 because it's 1 standard deviation above 6, right? The standard deviation length is 2, so if you go From 6, you go up 2, you get to 8. So that's 1 standard deviation. This would be converted to 2 because it's 2 standard deviations. This would be converted to -1 and -2. So that's what we mean by normalizing, or that's one way to do normalization. So the point I want to make is when you normalize your data based on taking the mean of your data and the standard deviation of your data. So the question is here okay, so what is this? What is this picture and what is this picture? So these are both cubes, and you can see that the one dimension is t, and that's the sequence length. That's an important thing, number in what we're doing, the sequence length, and that's what we have here. And c is the embedding dimension. That's very important. We said we might have an embedding dimension of 2, or we might have an embedding dimension of 3 or 768 or whatever it is. We have the embedding dimension that's called c. That's because this, I don't know, used to the kind of what do I want to say? It's kind of a holdover from working with convolutional neural networks. And this was the number of channels. And for some reason, they didn't bother to change this to like D for dimension or embedding dimension or something like that. So they use C here. So it's not so great, but that's why they use C. And then B is our batch size. Sometimes it's denoted as N. That's our batch size. So let's think about this cube. So let's say our embedding size is 6, right? We said we could have an embedding size of 3 or 2 or 768, but let's say it's 6. Okay, our embedding size is 6, and let's say that our sequence length is also 6, just to make things um, fit this picture. So our sequence length is also 6, okay? And let's say even our batch, and the number of elements in the batch is also 6. It doesn't have to be these numbers. This could be, the C could be 2, and T could be 8, and B could be 10. They could be any numbers. But let's just assume they're all 6 just right here because that's what this picture shows. So, okay, but going back to this, when we normalize things, we have to decide, what the data is that we're not. I have to calculate the mean of something. I have to decide what am I calculating the mean of. So the difference between doing what they call batch norm and layer norm is that in batch norm, um, we're not considering all of the data. So each one of these represents a number. So like, let's go back to this one more time. So this is a sequence of length 6. So this is a token, 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 and this is a token. But each token is is represented by embedding, and the embedding length here was 6. So this is the first embedding, and this is the second embedding. I'm sorry, this is the embedding for the first sequence. I'm sorry, first token, the second token, the third token, the fourth token, the fifth token, and the sixth token. But this here is just the first batch. Then we get the second batch, which is here. And then we get the third batch, which is here. So each layer, so the first layer here, is one element of our batch. The second, remember, each element of our batch is a whole sequence, a whole sentence or something. So this is a whole sentence. It has 6 words in it. So this is the first element of our batch. This is the second element of our batch, the third element of our batch, the fourth, and so on. Same thing here. Now, we have to decide, again, I'll say it again, what we're going to calculate the mean of. So we don't do it for the whole cube. That's not what we're doing. And there are some reasons for why we choose to do one way or the other, and I'm not really familiar, and you should look it up and see what kind of the use cases for doing the batch norm versus the layer norm. But anyway, in the batch norm, what you do is you use this slab and you use all the numbers in here and then you calculate their mean and their standard deviation, and then you rewrite all these values according to that. Just like I wrote, this was 6 was 0, and this was 1, and this was 2, and this was -1, and this. So I rewrote all of those. You're going to do that with all these values in here, according to just what's in here. And then you're going to do it again for this layer, according to what's in there. And then you're going to do it again for this layer, and so on. So when you calculate the batch, when you do the batch norm, you're doing it this layer, then the next layer, then the next layer, and so on. And that is batch layer. And if you're doing, I'm sorry, batch norm. And if you're doing layer norm, then it's this way. So you don't take this set of values for the first calculation of norm. You take this set of values. Okay? So it's different. And obviously you're going to get different values when you do the transformation. You're going to transform everything in here, then everything in here, then everything in here, then everything, and so on. So all these numbers are going to become new. But if you do it this way, you don't expect that you're going to get the same set of numbers that you get over here in each of these cubes, or little cubes. So I'm trying to figure out why you call this one batch and this one layer, because I sort of think I would want to call this one batch, because this is the first batch, and this is the second batch, and this is the third batch, so I would want to call that batch norm. But they're calling this one batch norm. Why is that? I don't know. I'm not sure. It should be the opposite, it seems to me. And what about layer norm? Why do we call something layer norm? So this is the first element in our batch, and then the second element in our, let's see, this is, I don't know, there's some way to say this. I forget how to think about it. But anyway, this is what, one way of doing it is called layer norm, and the other way of doing it is called batch norm. And as we said, note that this slab here represents a single training example, right? It's this represents one sequence, like one of the sequences that we were just talking about, like up here. Like every effort moves you, except that we need 6 words, because that had 6 for the sequence length. So we need 6 words. But anyway, it represents, this slab represents one training example. Okay, so anyway, I'm not quite sure why this one is called batch and why this one is called norm, a layer norm, sorry, layer. But nevertheless, let's read this. So now let's implement layer normalization. So that's what we're doing in our case. We're not doing batch normalization. To improve the stability and efficiency of neural network training. So the main reason the large reason for doing this is that it will improve our training in terms of stability of the updates and the efficiency of the neural network training. The main idea behind layer normalization is to adjust the activation that is the outputs of a neural network layer, to have a mean of 0 and a variance of 1. Okay, so I didn't quite say it that way, but I gave you the right idea. Also known as unit variance. So, okay. This adjustment speeds up the convergence to effective weights and ensures consistent, reliable training. In GPT-2, the modern transformer architectures, layer normalization is typically applied before and after the multi-head attention module. So, the reason they do this is they experimented with it, and it turned out to work better than not doing it in terms of how well, their outputs that we get from a given prompt are. And as we have seen with the dummy layer norm placeholder before the final outputs layer, okay, so we know that we're doing it here, here, and I think here also. Okay. So let's read that again. In GPT-2 and modern transformer architectures, layer normalization is typically applied before and after the multi-head attention module, and as we have seen with the dummy layer norm placeholder, before the final output. Okay, we just saw that. Okay, now this figure provides a visual overview of how layer normalization functions. So let's read these comments. The input of this diagram and the output are of size 5. Is that true? This is 5, and this is not 5. So that's wrong. Okay, the output is of size 6. Not sure why he does this. Okay, sometimes he... Okay, this is essentially the current representation of a single token. So this is just one token, I believe. Yeah, it says a single training example. It says a single training example. Okay, let's not get caught up in the size and even whether this is a single training example like he says, or if it's just a single token, and these are the embedding values, because typically, right, we have embeddings. We don't have just a single number to represent one, unless we're talking about that. I don't think so. Anyway, let's not worry about that. But we've got 5 here and 6 here, and then we're going to apply layer normalization. And when we do that, first of all, we can check the mean and the variance here, and we get these numbers. And then we apply layer normalization, and what we hope for wasn't exactly the same transformation that I was showing you earlier, where I gave you the numbers 2, 4, 6, 8, and 10. Or maybe it was, I'm not even sure. But anyway, here, when we do this layer normalization, at the end, we're going to have a mean of 0 and a variance of 1. Okay, so that's the point of doing layer normalization. So I'm not quite sure what this means. He calls it a single training example, but that's very weird, I think. But he does do some strange things here. Okay, let's keep going. Okay, so what he's going to do is just do a little experimentation here. So he creates like a fake batch example, which has 2 rows and 5 tokens in each row. Okay, and that's called the batch example. And now he's just going to apply a linear layer to that, and then a ReLU. So this is just playing around. Okay, so he puts he creates NN sequential and calls it layer. So that's our layer, and it consists of this 2 things. It has a linear layer and then a ReLU. Okay, so that's called layer, and then he's going to put the batch example here into layer and print it out. So just playing around now, and when you do that, we get something like this, which is what we expect, because the input was 2 by 5, but the linear layer expanded it to 6. Okay, now you might wonder why did he do that? Why did he expand it to 6? He's just playing around, so just let him do it. So we're going to supply our linear layer and then the ReLU, and we have 2 elements in our batch, so we should get 2 of these, each with 6 values in it. That's what we get. So he says the neural network layer we have coded consists of a linear layer followed by a nonlinear activation function ReLU. Okay. Later we'll learn about other activation functions, but right now he's using ReLU. Okay, now he's going to do his own manual normalization. Let's see if he does what I said. So he's going to take out, which is what we got when this is out. And so he's going to work with this thing. And now, we want to normalize it. Now, here we can still think about, like, when I calculate the mean first, am I going to calculate the mean of all the values? Or am I going to just do it like by row? So this one, and then a different mean for this one, and so on. Are we going to do it that way? Or are we going to calculate the mean of, like, by column, like these two, and 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 these two? So we have all of those choices. I'm not sure which one would be considered layer normalization here, but I know what he's going to do because I've read it already. And he is going to do this way and this way, and I guess this is layer normalization. Anyway, let's see what he does. So what does he do? He takes out dot mean dimension minus 1. What does dimension minus 1 mean? It means the last of our dimensions. And here we only have a two-dimensional object. This is like a matrix. And we have the row dimension and the column dimension. The last one is the column dimension. So we're talking about the column dimension. So he's figuring out the mean per row, actually, across the columns. Okay, that's what he's doing, across the columns. So if he was doing it across the rows, then we would get one mean for this, one mean for this, one mean for this, this, and this. We get 6 means. If he's doing it across the columns, then you'll get, or per row, then you'll get just 2, and you'll see that he's just going to get 2. So that's what's happening. Okay, so he does that, and then he prints this mean. Oh, he also calculates the variance here, the out dot variance, and he calls it variance. And then he prints the mean and he prints the variance. So are we going to get a mean here, a mean here, a mean here, a mean here, 6 of them, or are we going to get 2 of them? We get 2 of them. So he's doing it across the columns, or we can say per row. Okay, and same thing with the variance. Okay, now there's one more peculiarity here, and that is, he mentions here, this argument here, keep dim equals true. So that was keep dim equals true here, keep dim equals true here. So what's that doing? Notice that when we got the mean, we really only need like a list, but we didn't express it as a list. We expressed it as a matrix, so to speak, or a two-dimensional tensor, so to speak. We really only need like a one-dimensional tensor, like just, but that's not what we're doing. We're expressing it as a two-dimensional tensor, and the original input was also a two-dimensional tensor. So if you want to keep that, so you can see here that this has 2 square brackets and 2 square brackets. You don't really need that to just convey this information, but he wants to keep it in that form, and that's what keep dim equals true does. So same information, it's just, are you calling it two-dimensional object or one-dimensional object? One-dimensional would mean a vector, or two-dimensional would be a matrix, and we're calling it a matrix or a two-dimensional object, and for some reason we want to keep that form. So that's what keep dim equals true does. So we could have done it just like this, but that's not what he wants in terms of what he's going to use it for. So I don't really like this language, but he says the dim parameter specifies the dimension along which the calculation of the statistic, the mean, or the variance should be performed. Well, I don't know, does that mean the dimension along which it should, does that mean the column, or do we call it the rows? I really don't understand that language. But anyway, it is per row, or we can say across the columns. Okay, so unfortunately, that's the way our language works. So we could have done it the other way, calculated the mean here, but that's probably not what we're interested in. or at least that's not what he's interested in. So he says, explains this here. This is because -1 refers to the tensor's last dimension, which corresponds to the columns in a two-dimensional tensor. Later, when adding layer normalization to the GPT model, we're not doing that here at all, right? We're just playing around with these numbers and just writing it through. This has nothing. We're just playing around here. We haven't done anything in terms of coding our layer class yet. We're just experimenting here. But anyway, he says later on, later, when adding layer normalization to the GPT model, which produces three-dimensional tensors because they all have batch, sequence length, and dimension length, or embedding length. So they're three-dimensional tensors. We can still use dim equals -1. I guess because we're doing it across the whatever, for normalization across the last dimension. Avoiding a change. So we're going to, I guess what that means when you say across the last dimension is we're going to have like when this is 1 and when this is 2, you're going to calculate BT. When this is 0, when this is 1, then this is 2. Not 0, there's not 0. Maybe it could be 0, yeah. 0, 1, 2, 3, and you calculate these. Okay, maybe you can figure that out. I think I just figured it out. Okay, so he calculated the mean already and the variance, but that's not doing normalization yet. So what does normalization mean? I don't know. Is this what? Yeah, that's what I did actually. So you take out minus mean divided by the square root of the variance. The square root of variance means the standard deviation. That's what I did, actually, if you go back and review it. So that's the normalized values, and then he's going to calculate the mean and hope he's going to show us there when he calculates the mean that it will be 0, and he's going to calculate the variance and show us that it will be 1. So it's doing what we said we wanted to do, and yeah. So these are the normalized values, and when you calculate the mean, it should be 0. Yeah, these are very small numbers, so there's basically 0. And when you calculate the variance, they're basically 1. So again, he's just playing around here, just experimenting with all this, kind of showing us that how normalization works in general, like just on a set of numbers, but not coding it into the layer norm class yet. And he's doing all this so that he can show us that he can create his own layer norm class, or that we can create our own layer norm class, and that's going to be here. But then, actually, PyTorch has a layer norm class, so probably we wouldn't even use. So here, you can access that as nn.layerNorm, and we can either use his class that he's going to code here. In fact, I think I'll stop with doing this. You can go through this. That's what he's doing. He's coding his class now, and then you can use that class, or you can use the built-in one from the NN module, and we can compare them, and his custom implementation versus the PyTorch built-in one. And in terms of performance, his is obviously going to be slower than what they do in PyTorch, where they can build things in C. And then a couple other comparisons here. So let's not get stuck in this anymore. So you can go through this yourself and see how he by the way, EPS here stands for epsilon, and in math, epsilon usually means like a very small number. And here we are going to use a very small number here in the divisor. So when we're doing a division and we're taking the square root of the variance, what he's afraid of is suppose the variance is 0. Seems unlikely, but it could be very close to 0, and if you take the square root, who knows? With rounding, it could be 0. So he doesn't want to run into an error because he was dividing by 0. So he just adds a tiny small number here in the calculation for every time he uses this layer norm. He's going to add in this tiny small number, but that's going to prevent him from dividing by 0. So that's what's happening here. And you can go through the rest of it and see. And he says, oh, there's 2 other parameters that he includes in here. And these are actually used here and here. This is like not what we did. He takes this is what we've been talking about, taking x minus the mean, taking the square root of the variance, and that gives us the normalized value. But then he doesn't use that strict per se. He takes the normalized value and then he has this thing called scale, multiplies it times that, plus shift, and he calls these are trainable parameters, trainable parameters. So I guess you can, when you do the training, these numbers can be trained, and maybe that can improve your performance. So I don't know. I haven't seen that before, but maybe some people have experimented with it and that it's useful to do that. Okay, but we're not going to go through that. And he says bias variance. This is just from statistics. It says our variance calculation method, we use the implementation detail by setting unbiased equal to false. And that means from statistics, sometimes when we calculate the variance, we use n minus 1, but we also use n. It's just an old concept, or a very basic concept in statistics, and he's just pointing that out here. And then he runs his class here, and he gets some answers here. And okay, so that is the end of what we're going to say about layer normalization. Except that here are 2 videos that you might want to look at. So here's one of them.
The art
So this one
API.
is what is
If you
layer
like
normalization?
go ahead and get your free.
There are a bunch of problems with batch normalization. So the first one is that
And this one is same channel, but batch normalization. So these are, you might want to take a look at those 2 videos.